Well, hello everyone, and thank you for joining us for today's session in our AIEI webinar series on high polymer modified asphalt binders and mixtures, a strategic look at implementation opportunities. We're at the top of the hour, so we'll go ahead and get started. My name is Tim Aschenbrenner. I'm with the Federal Highway Administration. I work in our headquarters pavement materials program. And the webinar today is going to present the latest insights from a national gap analysis of high polymer modified asphalt binders and mixtures. We're going to draw on in-depth visits we had with leading states, including New Jersey, Ohio, Oklahoma, Utah, and Virginia. And we'll look at some of the challenges and opportunities associated with implementing these high polymer binders and mixtures. We'll talk about some real-world case studies and agency specifications and findings to help practitioners make informed decisions about implementation in your area. Before we begin, I'd like to go over a few housekeeping items. Please keep your microphone muted during the webinar. If you have any questions, please post them in the chat box, which you can access by clicking on the chat in the meeting controls. I'll compile questions during the presentation, and then the presenters will address them at the end of the webinar as time allows. Any unanswered questions due to time constraints, we'll go ahead and respond to those separately. Now, this webinar is being recorded, and a link to the recording will be available on our AIEI YouTube channel at a later time, usually about 1 or 2 weeks. And all the webinars in our series are at that link. We have a few disclaimers. This project is sponsored by the Federal Highway Administration and University of Nevada, Reno Cooperative Agreement. This is not meant to bind the public in any way. It's provided for informational purposes. And you'll probably recognize some products or manufacturers. They're not an endorsement, but they're just provided for informational purposes. And then all AASHTO and ASTM standards you see mentioned are private and voluntary, and they're not required under federal law. We have 2 slides for acronyms and abbreviations. These should be handy when you watch the recording. You can refer back to this if there's any acronyms you're not familiar with. And here's the second slide of those. We do have expected outcomes. So at the end of this webinar, we certainly hope that you'll understand how high polymer binders and mixtures are defined, specified, and used across different state DOTs. We hope you'll learn about key benefits and limitations, including cost, performance, and constructability considerations. We'll explore the results of a SWOT analysis, the strengths, weaknesses, opportunities, and threat analysis that identifies barriers to broader adoption and potential solutions. We'll review case studies highlighting how high polymer binders are being used for thin overlays, structural application, and preservation strategies. And we'll discover implementable strategies and specification requirements that agencies can adopt to ensure successful deployment. So meet your moderators. They'll be myself, Senior Asphalt Pavement and Materials Program Manager with FHWA, as well as Professor Ellie Hodge from the University of Nevada, Reno. And then meeting your speakers, presentations today will be delivered by Dr. Johnny Haboush from the Asphalt Institute, a regional engineer who covers the West. Dave Johnson, also from the Asphalt Institute, a senior regional engineer who covers the mountain area of the United States. I'd like to mention the statement of work co-leads, Dr. Ilker Boz, a senior research scientist from the Virginia Transportation Research Council, VTRC, and he's also joined by Dr. Stacy Diefendorfer, an associate principal research scientist from VTRC. They co-led this effort along with Johnny and Dave. And at this point, I'll turn it over to Johnny to get things started.
Thank you so much, Tim. Hello, everybody, and again, welcome to the webinar entitled High Polymer Modified Asphalt Binder and Mixtures, a Strategic Look at Gaps and Implementation Opportunities. First of all, I would like to express some acknowledgement for a lot of people who were key in contributing to this effort, starting with the Asphalt Institute leadership and engineers, the personnel from New Jersey DOT, Ohio DOT, Oklahoma DOT, Utah DOT, Virginia DOT, as well as the subject matter expert from the Federal Highway Administrations. The first question that we got to ask to kick off this webinar is why we modify asphalt with polymers. And this stems from two primary advantages. The first one is about improving rotting resistance, and that's at a high temperature by enhancing a lot of the high temperature properties. And then the second will be improving cracking resistance by increasing flexibility and energy dissipation, and that happens at intermediate and low temperature. With polymer modification, we have tendency of extending the useful temperature interval, UTI. However, this is highly dependent on the polymer type as well as the polymer level. It's always been about striking the optimal balance between providing enough stiffness to resist rotting and flexible enough to prevent any type of cracking. Again, polymer modification led to a significant improvement in balancing stability and durability. This is a couple pictures of an unmodified binder versus an SBS modified asphalt binder. And then the image courtesy are from Creighton. So the first on the left is an asphalt binder that was unmodified, neat, that was poured, that beam was poured. And then when you modified that, it loses its shape permanently. However, on the right, this is a sample of an asphalt binder that was modified with SBS, and it retains shape over time even under stress. Polymer modification is not new, and there's been a lot of work for over 50 years just looking at this technology and polymer modification in general. I want to highlight an effort that was done by the Asphalt Institute back around the 2005, and it's entitled Quantifying the Effects of PMA for Reducing Pavement Distress. And then the intent there is to compare the performance of neat hot mix asphalt mixtures to that of companion sections built with one or more layers of polymer modification. The results showed how a typical maintenance and rehabilitation schedule for unmodified pavement could be extended with the use of polymer modified asphalt. It's either in just the wearing course or both the wearing course and base layer. If you want to learn more about this effort, we're providing QR code for this slide. Also, another effort that was worth mentioning as part of this effort is about the use of polymer modified in dense graded mixtures, and that's internet survey and tools to measure return on investment. And then the intent of that effort was to recommend one or more tools that highway agencies can use to ensure that there will be a sufficient return on investment when using PMAs in dense graded mixtures. And then this was part of an effort that was funded by Federal Highway Administration and NAPA under cooperative agreement. When this study was initiated back in April 2018, NAPA reported while some states are only specifying polymer modified on highways with heavier traffic loads, other states were beginning to specify it for all dense graded mixtures. Since the latter change in specifications would usually increase initial pavement costs, it was felt that tools such as performance predictions provided by mechanistic empirical analysis, compared with the life cycle cost analysis, LCCA, should be used to ensure that these increased costs will translate into better pavement performance and hence less applications of pavement preservation or rehabilitation strategy during pavement service life. The concern expressed by some industry members was that some highway agencies that have recently increased the amount of PMA being used or were currently considering increasing it have not used any tools to ensure that there will be sufficient return on investment. Now, the major question is what makes an asphalt binder labeled as a high polymer? And that definitions may vary depending on several factors. The first one is the polymer type. The second one is the polymer content. And that's if we take a conventional polymer modified asphalt, this one is typically modified with about 3% polymer content, plus or minus 0.5%. When we start pushing towards that high polymer loading, we're talking about a 5 or 6%. And even in some case, especially when we're using proprietary product, we start talking about that 7 and a 7.5%. And then the final properties of your blend between your base binder and your polymer is highly dependent on the polymer content itself. So if we see in the chart that we have or the graph that we have, at a lower polymer loading, we see an asphalt continuous behavior of the final blend. When we're pushing beyond that 3%, we start seeing that co-continuous behavior between the base asphalt as well as the polymer. And we see more of a polymer continuous behavior when we start pushing these high polymer content level above 6%. All of that to get us into what we're trying to do as part of that effort. So high polymer modification also is not new. It's been around for about 14, 15 years, even a little bit more. So we wanted to conduct a gap analysis on the use of this technology in binders and mixtures and try to identify critical limitations, gaps, and need through what we call a SWOT analysis: strengths, weaknesses, opportunities, and threats. The main intention is to identify and put forth effective strategies and lessons learned by state DOTs. And these are the 5 states that Tim mentioned that we had the pleasure to visit with and learn from their experience. And also this effort build on a previous effort that was completed under the Federal Highway Everyday Count a Thin Overlay Pavement Solution Program, EDC6 TOPS. High polymer modification was found to offer additional advantages in flexible pavements subjected to heavy and slow-moving traffic. When we talk about new construction, the consideration is to combat distresses, critical distresses such as fatigue cracking, rutting, shoving in asphalt, as well as top-down cracking. And in case this technology was used for rehabilitation, the consideration is to combat what we call reflective cracking. Going a little bit internationally for some of the main case studies that happened, we're starting with the Port of Napier in New Zealand in 2010. The use of HP provided a long-term solution to the frequent rutting issue they had at the port facility. This was paid back in 2010, and it delivered an exceptional rutting performance, especially for heavy load traffic versus other alternative solutions that were considered. Another great example was at the test track for the National Center of Asphalt Technology, the NCAT test track located in Auburn, Alabama. And that was one of the first sections that were built in United States back in 2009. And then a recommendation is to use an AASHTO structural layer coefficient 70% higher when you're using a certain technology under the high polymer umbrella. So the section was built back in 2009. It was subjected to multiple cycles of traffic, and it provided an excellent performance. And then if we take a look at the pavement structure here, we see that a 7-inch structure was equivalent of about a 5 3/4 inch of HP mixtures. This did not stop here. Other state DOT expressed interest in trying to compute structural layer coefficient and do a structural assessment for their pavement when HP technology is used. For example, Florida DOT recommendation was to use a 0.54 structural layer coefficient compared to a typical 0.44 for PMA. This was developed based on performance properties of the binder and the mixtures and using mechanistic empirical simulations and analysis, taking into consideration several critical distresses such as bottom fatigue cracking, rutting, shoving, and reflective cracking. Also, the NCAT test track has a lot of of follow-up and studies, whether in sections and analysis between 2010 and the 2015 on top of the 2009. And then they recommended structural layer coefficient up to 0.75 and 0.92 when HP mixtures are being used, compared to the 0.44 and 0.54 conventional use for PMA, respectively. And all of that was determined based on in situ strain measurements and a lot of lab fatigue performance. Staying as well in the field, we go to New York City first read in 2012. So we had a high polymer thin overlay that was built over existing concrete, and it saved about 80% in cost versus removing and replacing. And then there is a photo that was taken and published in the TR News in 2009, and then that shows a great performance of the section. Another interesting project goes into Oklahoma on the I-40 in 2012, and the use of such technology eliminated rutting issue, and it was awarded as perpetual pavement by conversion. And then later on, as part of this presentation, we'll talk about the rich intermediate layer, the RIL, and that's a type of mixture being used by Oklahoma DOT with an HP binder. Again, that section was paved in 2012, and then it shows an international roughness index of 50 even after 10 plus years. Going down southeast to Tampa, Florida in 2016, the HP technology delays appearance of cracks in an overlay. It was paved in May 2016. After 2021 inspection, it was shown that there is over 20% total cracking with the conventional PMA in that lane versus less than 2% total cracking with the lane that employed high polymer modified mixtures. Going up to Alaska, HP offered a solution for studded tire damage, and then the typical binder used in that state when it's labeled HP is a PG64E-40, and it reduced rutting by almost half compared to previous, alternative or previous binder using other alternative. Also, the use of HP was even analyzed for Florida DOT into their open graded friction course, and that was an effort that was completed by a Texas Transportation Institute, TTI, and it showed that the use of HP in open graded friction course can even enhance that performance of that technology by about 7 to 8 years in terms of performance life or service life. And a lot more of examples that are available. If you're interested, the upper QR code will take you to a more practical or practice-oriented type of an article summarizing all these technologies as well as the various strategies to structurally assess this technology. If you're interested more in learning about the lab and the field insight over the last 10 to 12 years, the lower the QR code will take you to a great article that has a critical review of such technology. So talking about the state of the practice, back in 2021, a project was initiated to look at that state of practice of using such technology in the United States. And then if you notice, we had about 20 states have had some experience with high polymer. And you will notice that the major focus is more towards the eastern side of the United States and primarily in the Northeast. QR code is provided to the document that has all insights on how the survey was conducted, as well as how the collected data was analyzed. As part of this effort, the first task of this effort consisted of reviewing the state DOT specifications. So with the help of the Asphalt Institute regional engineer, we went ahead and we computed all specifications that may exist in the United States. Please note that this map is as accurate as of 2025. You will notice that there is an increase from that 20 states to about 30 or 31 states. You will notice two types of coloring on the map. The ones in the red are the ones that follow the AASHTO M332, and then that evolved the use of the MSCR, the multiple stress creep recovery test, while those that are in green represent states that do typical PG grading according to AASHTO M320. You will notice 5 yellow stars. These refers to the 5 states that we had virtual visits with, and we compiled their practices and got insights and lessons learned from them to be able to build that SWOT analysis. So overall, you will see a huge increase from that 20 to 30 state. Probably if this is to be repeated in 2026 or 2027, we'll have even more increase in the number of states trying to experience such type of technology. Taking a brief look at the type of specification, these are the specification from the 5 states that we visited with. I want to talk first about the last one, Virginia. So Virginia follows an M332, and that's a PG76E-22. They do have a requirement in testing for the MSCR. The non-recoverable compliance at 3.2 kPa is a maximum of 0.1 kPa -1, and they have a requirement on a percent recovery of a minimum 90% at a 76 degrees C. While we go to another example, for example, Utah used the Astro M320 with the PG76-34. They only have a requirement on the percent recovery of a minimum 90%. They do have a requirement on their Delta TC, but we will notice as well throughout the case study, they do have requirement as well on the mixture and not only on the binder. So all what I'm trying to say is the definition and acceptance of HP is not related to SBS polymer content, but it's more, or it is a performance-oriented viewpoint. So the definition is related to specific binder rheology-related parameters and characteristics. Getting us through next is the second task was to develop an information gathering document. So we developed that. It had about 30 questions broken into 9 models. And these various models covers practice, usage, specification, mixture pavement design, environmental restrictions, research, even projects, costs, tonnage, benefits, implementation plan, and additional information. And we were blessed that the personnel of these state DOTs were very generous in the information that they provided, and they were instrumental and key contributor to the success of this effort. So what we're gonna do next is we're gonna go through insights from these 5 virtual visits from these 5 states, and we're gonna start with New Jersey, and then with that, I'll hand it to my co-presenter, Dave Johnson.
All right. Thank you so much, Johnny. I see that we have folks continuing to roll in. It's great to see so many people expressing interest in this. So as Johnny rightly said, we're going to hit New Jersey first. We're going to spend a little bit of time on these first few states, and then I'm going to eventually make my way to Utah, no pun intended, and give you some more detail on that particular state, at which time I'll turn it back over to Johnny to hit Virginia and lead us through the rest of our webinar today. So New Jersey has a long history of utilizing highly modified materials. Their primary usage is around bridge decks, but as well as bridge decks, they're also utilizing the highly modified materials on thin overlays in some key high performance areas. Their key distress that they are working to combat is fatigue cracking and also creating impermeability. As you might suspect with bridge decks, that's very important. They are utilizing a fine graded mix with low air voids. And I'll pause there for a moment. You'll notice that there is a bit of a trend in that relationship. Both fine mixes and low air voids is a reoccurring theme in the 5 states that we visited. They do find that this is a cheaper option for them as compared to other alternatives. However, if you compare it to other polymer modified mixes in the state of New Jersey, there's nearly a third of a premium that they're paying at about 32%. If we look at the mix design, whether it is the ultra-thin performance overlays or the bridge deck waterproofing overlays, you're going to find that they're designing these on a gyratory compactor with 50 gyrations. The asphalt binder content is intended to be very high at a minimum of 7%. They do have specifications for the bridge decks of 9.5 as well as 12.5 millimeter mixes. For the ultra thin toppings, they have 4.75 as well as the 9.5 millimeter mixes. They do have very high density requirements for both technologies, although the requirement on the bridge deck is even higher, with a range of 98 to 100%. So very close to zero air voids at the upper end of if they're hitting that sort of level. And with the overlays, the thin overlays, they're targeting plus or minus a half um, a percent, 95.5 to 97.5%. Both have very high VMAs at a minimum of 18. The voids filled with asphalt are also very high. Uh, some fairly typical dust to binder ratio ranges on the overlays, but low ranges on the bridge decks. They do have a drain down test, which many folks in dense graded mixers, that is a uniqueness, but we will see that also pop up once more with another state. In New Jersey, for their rutting performance, they look at the APA as their tool. They are testing that at, as we can see, at 64 degrees C, a standard 8,000 loading. No more than 3 millimeters of rutting is allowed. They do beam fatigue testing on the bridge deck at 1,500 microstrains at 15 degrees C, and they need to exceed 100,000 cycles on it. For the thin overlays, they're relying upon the overlay tester developed in the state of Texas at 25 degrees C. And you can see that they also have a pretty high requirement there and has to exceed 2,500 cycles. So that is it for New Jersey. Let's move on to Ohio, where they as well are using these highly modified materials for bridge decks, but also at some key intersections and high stress areas. The binder that they use is a PG 88 minus 22 modified. It's going to be pre-blended with modification, but there are no requirements placed upon their suppliers as to what kind of polymer nor a particular polymer loading. They are utilizing the PG Ashto M320 with an elastic recovery of at least 90%. They have a separation requirement of no more than 10%, and the rotational viscosity has a relatively high, compared to most PG binders, allowance of no more than 10 Pascal seconds. In terms of cost considerations, the size of the project certainly comes into play historically in the state of Ohio as to how much of a premium. In the case of their larger projects, it's a smaller premium of 7 to 10%. On their smaller projects, it is, as expected, a higher premium of 10 to 20%. Lots of things are coming into play as to influence that cost. The plant setup, the tonnage, and the project type are three that they noted of particular interest. Looking at the usage history, we can see that they have over a decade of usage beginning back in 2014. Fairly low tonnage for a number of years until there was a notable uptick in 2017. And as you can see, there were 10 projects, 7 bridges. 2 of the 10 projects had what they considered significant tonnage. And we, again, saw that total of over 100,000 tons. The only other year that 100,000 tons were exceeded were just a couple of years ago in 2023. But notice that there were only 4 projects, which included only 1 bridge deck. So the tonnage totals in 17 and 23 were somewhat similar, but the number of projects to produce that tonnage were notably different, and the distribution of those types of projects was also seen to have been different. In terms of the job mix criteria in Ohio, they are also having a minimum binder content, also very high in their case of 7.25%. Gyrations are at design, again, at 50 with an Nmax of 75. The design air voids is 1.5%. The VMA on their mixes is 15.5. They do have a permeability requirement, which in bridge decks is very common. We want to have that low permeability. Rutting is a maximum of 4 millimeters, and we can see that they are also using the APA, and the requirements you can see down below again at 64 degrees C. They also have a flexural beam requirement, which is identical to what we saw in New Jersey, 100,000 cycles at 1,500 microstrains, with the specimens designed and built to 4% plus or minus 1% air voids. There is research that's going on in the state of Ohio that looked at how much of a performance boost do we see with these mixtures compared to other options, the conventional binders. And they found that it was about a 25% increase in life. So about 25% over their normal of 12 years would mean that they're getting about 15 years or more out of these sections. Moving on to yet another O state, this time Oklahoma, where they are using these, as Johnny already mentioned, is commonly as a rich intermediate layer in very high strain environments. What they are looking to address is reflective cracking. They believe that the solution that they're finding success with is this very rich, fine mixture designed to low air voids with a high binder content. They find that this is a lower cost than a thick structural layer or the utilization of geotextiles plus a leveling course. But the cost increase is a little bit less than what we saw elsewhere. In this case, about a 21 to 31% cost increase. So they are definitely paying a premium for them, but the return on investment is being seen in the performance. In terms of mix design, again, a 50 gyration mixture, keeping the binder content not quite as high. They have a minimum of 5.5% on their 9.5 millimeter mixes. They are designing to a 3% air void at percentage of GMM. Their BMA is the 15.5, as we saw in Ohio as well. VFA is 73 to 79. It's interesting. They also are doing a TSR. This is the first state that we've seen that is looking at that, and they have an 80% requirement. They, as well as others, are utilizing the Hamburg. They are using their standard 50 degrees C's, 122 Fahrenheit, and a maximum of 20,000 cycles on that. 12.5 millimeters of rut, excuse me. The cost increase is strictly in a cost dollars per ton. Recognize that they are looking at their mixtures from a unit cost. Some of our states pay for binders separately. Some pay for the mix as a unit of aggregate as well as binder, which is consistent with what Oklahoma is doing. And we've noticed that there was a trending upward in terms of cost, with a peak of the values that we have available to us in 2022 of a little over $165 a ton. There was a reduction of almost $9 a ton seen in 2023. But notice that the approximate difference in price has continued to climb for most years, with a most recent premium of about $30 per ton above their conventional polymer modified mixes. We're going to spend a significantly greater amount of time in Utah. Utah has really pioneered a unique mixture that is gaining a lot of attention both stateside as well as internationally. The work that is done there, Mr. Howard Anderson, who was recently promoted to the statewide materials engineer, is the individual who deserves a significant amount of credit for this, as well as others on his team, as well as, I must say, the industry. There's a very good synergy between the contracting community and the DOT in the state of Utah, in no small part because of the relationship that the Utah Asphalt Pavement Association helps to foster. Utah is a Hamburg state. They were one of the lead states way back when the Hamburg was first introduced in the United States, and they continue to utilize it. They did a lot of their investigative work at the laboratory with the Hamburg device. They made samples of various asphalt contents, typical super pave mixes designed to a typical 4% air void value. They were running the Hamburg initially at their standard temperature of 50 degrees C for 20,000 passes, but then they would increase the load on each of the wheels and run an additional 20,000 passes. And after a full 40,000 passes, they would allow no more than 10 millimeters of rutting, which, by the way, is their standard maximum for mixtures at 20,000 passes, 50 degrees C, and standard loading weights. They were very satisfied with what they were seeing in the laboratory from this Hamburg work. In fact, they reported no failures at 40,000 passes all the way up to the 6.8% binder content. But the initial projects that they went to the field with were typical super pave projects where they did a substitution of a 6434 binder at design and substituted in the highly modified 7634 binder. Both of those were constructed on secondary highways in 2017, done to typical lift thicknesses, and the performance has been no reported distresses of any significance thus far at almost 9 years of service. Being happy with that work, work continued within the lab, and Howard Anderson and his crew continued to refine their specification. And this is the current binder specification for the 7634 binder. Note that on the original binder, they have a G-star requirement, minimum of 1.3. In this case, that test is run at 76 degrees, the high PG grade. That is a consistent requirement for all PG grades in the state of Utah. They conduct the test at the high PG grade, and they have to have a minimum of the unaged material of 1.3. There is a high temperature delta requirement of a maximum of 71 degrees. After it runs through the rolling thin film oven to simulate what may happen at the hot plant, you can see they have some typical requirements, including an elastic recovery conducted at 76 degrees of a minimum of 90% recovery. They continue on with your typical PAV requirements to simulate some longer term aging in the field. And the one of note that we like to point to that is a little bit unique in the state of Utah, but not exclusively, is looking at a Delta TC, where they have a requirement of a minimum of -1. Howard is always doing a great job of trying to provide a visual for folks of what exactly some of these engineering parameters might relate to. And in terms of what is a kilopascal, he went through the calculations and found that approximately 11 dimes equals approximately 1 kilopascal. And so he had the folks in his lab create some cups. You can see that they were placed at room temperature, which is consistently somewhere around 72 to 74 degrees Fahrenheit. And over time, in fact, in over 14 days, they just simply let that material set. They did time-lapse photography. We can see the initial photograph on the right and the final photograph after nearly 14 days on the left. And notice the differences between these materials. When we look at the far left material, that is a neat asphalt. It's a 58-28. We have progressively higher polymer loadings for the 6434, the 70-28, and finally the highest polymer loading in the 76-34. And notice that after 14 days, the evidence of the dimes is at best minimal. You may be able to look real close and find a dimple on the surface of that -58, but essentially it swallowed it up. The typical polymer loadings, both of these are about a 3.5% or so polymer loading. We can see that the dimes over time, 14 days once more, at room temperature, slowly made their way in, but they're still visible. But very impressively, the 76-34 after 14 days, while it has deformed slightly, it is very minimal by comparison. So armed with all of this information, Howard was able to get approval with the higher ups at the Utah DOT to establish a field trial. The regional materials engineer for Region 2 in the state of Utah was entrusted with the selection of the location, and he picked what he deemed to be the most challenging location within Region 2. So for those who aren't familiar with the state of Utah and their regions, think of the Salt Lake City area and move east and west across the state, and that is where Region 2. So if you move across to the west, you'll find the port of entry on the Nevada border at Wendover on Interstate 80. While the average daily traffic at that location isn't exceptionally high, as we can see a little under 8,000 vehicles per day, it is a very major truck route with over half of the traffic stream actually being the heavy commercial vehicles. When you equate that to equivalent single axle loads, you'll find that it's north of 2 million per year. This is a very warm location within the state. And if you were to run the typical software at a 98% reliability, you would see that a PG 64 minus 28 would be the recommendation from that software. So in the case of the 7634, we're stretching the boundary on both the upper and the lower end. The project itself is not a very high tonnage. This was a trial. Around 330 tons is all. It was an existing Portland cement material. They milled out 6 inches, and in one lift, they replaced it with this highly modified material. One of the reasons that this location was chosen, as I mentioned, it was one of the most challenging. At this port of entry, the DOT had seen notable struggles to keep material, both asphalt and concrete, long term. Admittedly, the concrete was giving them more years of life than the previous asphalt mixtures, but they were hopeful that this mixture might give them superior performance. I say that they were hopeful, but I will tell you that the individual who selected this, he had a significant amount of money within the budget because he anticipated that it would not perform. He thought that the incredible truck traffic that they have there would prove to be too much for this mix. And so he actually had $300,000 in the project to mill and remove that material when that fall, as he thought that it would not succeed and to be replaced with Portland cement concrete. As we'll see, that caution proved to be unnecessary. This is a dense graded mix, and again, that 6 inches was conducted in a single lift. And it's also noteworthy that this mixture was subject to about a 2-hour haul. The contractor is Staker Parsons, a CRH company that is a very high quality contractor. They have in fact won the Sheldon Hayes Award through Napa in the past as a testimony to the quality of the work that they do. This mix was produced just north of Salt Lake City at the Beck Street plant in Logan, Utah, and it was hauled all the way across the state to that western border, again, about a 2-hour one-way movement where the project location was. Utah's mixed design requirements now incorporate both a 12.5 and a 9.5, the half-inch and the 3/8 mixes. They are also designing to 50 gyrations. The target air void is plus or minus a quarter, surrounded by that 1%. So 3/4 to 1.25% is the range that they allow. The VMA, dependent upon whether it's a half or a 3/8 mix, have high values as well. What's very noteworthy is the voids filled with asphalt are high in the low 90s. The dust range, as we can see, is a fairly typical range. And despite the fact that they were once running 40,000 cycles at higher weight, they then shifted to 40,000 cycles, 20,000 cycles at the standard weight with 50 degrees C and an additional 20,000 with the bath temperature increased to 54. Again, at the standard weight, that 10 millimeter max requirement. Because of the results that they've seen thus far, the decision was made about 2 years ago to only do 20,000 cycles at the higher temperature of 54 degrees, maintaining that maximum of 10 millimeters. To date, whether it was 40,000 or 20,000, there has not been a mix that has had a problem. Much like we saw in the state of New Jersey, Utah also requires a drain down test on this dense graded mix. Again, that is to ensure that with this rich mix, we don't have an experience of bleeding at those higher temperatures and during production. And again, thus far, we haven't had an issue with any of the mixtures in Utah with that parameter. The mix design requirement for the Port of Wendover, again, was at 50 gyrations, excuse me. We can see the results of the Hamburg both after 20,000 at 50 degrees and then subsequently an additional 20,000 at 54 degrees. And you can see on this particular mix, even after those full 40,000, we were just a little over 6 millimeters of rutting. The VMA on this was at the 15.3, fairly close to the lower limit. Those who are involved with mixed designs, that's probably not a big shock that we would be close to that lower limit. The voids filled with asphalt then winds up a little bit over 93%, What's also noteworthy is that next line, the wrap. Historically, in the state of Utah, they have not allowed any wrap in their surface mixtures. This was the first mix that they did allow wrap at 15% by mass. That equates to about 12.5% binder replacement. It's also noteworthy, and it's not seen here, but they do not allow any natural sands, any natural material. It's 100% crushed material coming out of the quarries in the Wasatch Valley primarily. So 15% wrap is allowed, but no sand. Staker Parsons was very concerned and questioning their ability to get good density, full depth on a 6-inch lift. I would point you to a Mixbusters article that Dr. Buzz Powell and I did that talks about thick lift paving and the ability to get density. But Staker, wanting to prove to themselves that they could get density and also wanting to determine what might be the best procedure to achieve that density, mixed about 100 tons of material at their Beck Street facility. They placed it on top of what really is an unprepared gravel surface. They simply brought a blade in, broomed off the loose material after it was bladed smooth, and then laid this thick lift at 7.5 inches, uncompacted, to be compacted down to a full 6 inches. They have some other notable differences. Not only is this not produced and being laid on concrete, and being laid on an aggregate base, but unlike Wendover, there is no haul. Mixed production temperatures are rated about 300 degrees Fahrenheit. And so moving from the hot plant, which is just a little bit out of the site of the picture on the right, to the site is virtually no haul whatsoever. The conduction of that test strip went without a hitch in terms of getting density. They did run into some issues of feeding. As you may suspect, the amount of tonnage that you need to provide to the paver when you are laying a 12-foot wide mix that is going down at 7.5 inches uncompacted is very noteworthy. So if you are in the process of considering doing thick lift paving, much like Utah is doing in this case, or the state of South Carolina and some others have done, you need to have your trucking on its A game. And the problems that, as we'll see at Wendover, if you do have a hiccup in that trucking, can be notable. So they recognized that they needed to make sure that the next day when they went out to Wendover, the trucking was on its A game. What did we see at this test strip? Well, first and foremost, the target density in Utah is 96%. They were getting densities of 97+%. They were using regular rolling equipment. They did notice, as we saw in that one picture, that feeding material was a challenge to get enough material on site, even though in their case, remember, this was a zero haul situation. They definitely created a great plan for that next day. What was most surprising to me about this test strip was the fact that you had unsupported edges. It was laid down at 7.5 inches loose, compacted down to 6. I truly expected this material to walk out some under the rollers, and it virtually did not. There was incredible stability with a double drum vibratory roller hanging over the edge about 4 to 6 inches without that material displaying any sloughing of it, even under vibration. So no significant issues were encountered in terms of densification. So we go out to Wendover that next day. This is a shot taken from a catwalk that happens to be at the interstate between the way stations on either side of the highway in the east and west direction. In this case, we are actually looking to the west into the state of Nevada. You can see that they placed a tack coat. I won't bother to criticize that tack coat any more than what I just did there. This is looking east of the scale. And here's a couple of pictures from construction. Again, they're producing at about 300 degrees Fahrenheit, a 2-hour haul. The mix was losing about 25 degrees Fahrenheit when it reached the ground. Notice the incredible width of the windrow in front of that material transfer vehicle. And notice also the very fine densities that in general they achieved. All of the top half, the top 3 inches, were above 97%, approaching 98% on a couple of the cores. But also notice that the bottom half densities were generally high on cores 1 and 2, excuse me, 1 and 4, but in cores 2 and most notably in core 3, we see a downturn in density on that lower half. And the question is often asked, well, any idea what happened there? Well, I mentioned that you need to have your trucking on the A game. And while Staker Parsons had a fantastic plan set up to achieve that, they did have the Murphy factor of paving come in and bite them. And I don't mean the Tim Murphy. For those of us who have the privilege of working with Tim, I'm thinking more generalized Murphy. And what happened there is they had a truck that had, excuse me, a tire issue, creating a delay. And in the time of that delay, there was enough time for adequate cooling to create issues with the material transfer vehicle. Staker had redundancy already set up to where they had a second paver, they had a second material transfer vehicle, and extra rollers on site in the event that there was a problem. And so there was a quick switch to the second material transfer vehicle. All the time that took led to a bit more cooling than what we see in this photograph. And that's what led to that lower density on the bottom half of that one core. What have we seen in terms of performance? We continue to call this early performance, but in June we will hit the 5-year mark. What we found is that successful construction, even with that 2-hour one-way haul, was achieved. The densities and the DOT was holding the contractor to their PWL spec only on the top half of those cores. They, as we saw, achieved great density of above 97%, almost to 98%. After approximately 5 million trucks, and we will be getting 6 million before this summer is over, there's no discernible movement. There's no cracking, zero distress of any sort. This site has been performing very admirably. A question comes up about skid numbers. This, again, is 100% crushed material. While it is a fine 12.5 millimeter gradation, the skid numbers themselves are very good. There was a second site that they relatively quickly decided to try this mixture out. Staker Parsons once more was the contractor at this location. This is a site north of Salt Lake City, fairly close to the Beck Street plant that I've mentioned where the mixture is being produced. They were originally planning on removing and replacing the concrete with additional concrete. But the decision was made, the question was asked, and the decision was made, what if we were to simply overlay it with this material? Would we get good performance without having to go through the time and expense of removing and replacing that concrete? Excuse me. So they chose to lay down 3 inches of material. They hit their target of compacted thickness very closely. The average binder content was, again, real close to that 6% value. Their average VMA, as we can see, was a little bit higher in this case. We were 15.3 at the mix design. Excuse me, they were hitting in the field a 15.7 at this I-15 overlay. And again, it easily achieved densities above 97% as an average. And the spread on that, by the way, was also quite good. There was a planned overlay which they executed in 24, so about 1.5 years, roughly almost 2 years in to the trafficking of this location. They did overlay it with an SMA. At that time, there was absolutely no distress. Fantastic performance, even though we can no longer see the highly modified materials. If and when reflective cracking shows up, we'll definitely be reporting that to folks in future presentations. So here's some slides, pictures of that location. This is the start of the I-15 overlay. You can see just behind these vehicles, that's the existing concrete that was overlaid. They did mill the start and stop at that location for a good tie-in. Just some additional photographs. These are all roughly 1 year following construction. So as mentioned, after a couple of years, there was no notable distress. We did acquire some of the Utah mix, again, from the Beck Street facility, utilizing a proven 64-34 super pave mix and comparing that in beam fatigue to the highly modified option at low air voids. And you can see that in the boxed examples, we are looking at equivalent microstrain requirements of 475, 425, and a peak of 600. And notice that in every single incident, not too terribly surprising to myself, the difference between the number of cycles to failure is somewhere between 50 times to a little over 70 times. In the case of the 600 microstrains, it was 72 times more cycles at 900 and almost 14,000 cycles compared to just a little over 12,000 for a very good super pave mix. So the upshot is that in the beam fatigue arrangement, the performance of the high mod system is exceptional. So another project that we like to talk about that is in the midst of construction as we speak. There's an interstate beltway around the Wasatch Valley from and just south of the international airport at Salt Lake City is where this project is located on I-215. The original plan, once more, was to remove and replace existing PCC. The decision was made to do an alternate design, looking at rubbleizing the PCC in place and overlaying it with 5.5 inches of the highly modified material in 2 lifts, in this case, an 1.5-inch leveling course on top of the rubbleized material, and then a final lift of 4 inches. The upshot of the cost savings was roughly $40 million compared to the removal and replacement option. And so UDOT maintained the budget for this project, but they extended the scope, adding in 17 miles of ramp work. Granite Construction was awarded this project, $111 million project award, and they just have wrapped up the rubbleization in one direction and will be continuing with the overlay, which will be finishing in the next couple of weeks, at which time they'll switch over to the other direction and begin the rubbleization process. A very unique project in terms of cost savings comparison between one option and another. What have we learned in the state of Utah? Well, densities have not been a problem almost exclusively. I have density data for 42 projects now. Of those 42 projects, only one has not achieved the target of 96% density, and that particular project achieved 95.7%. And so even the one that didn't meet specs was still a very high density by conventional comparisons. Regular rolling equipment and procedures have been followed. I didn't mention out at Wendover as well as at the test strip, Staco Parsons found that with just 5 passes of the double vibratory roller, they were getting all the density they need. Therefore, they did not include an intermediate roller rolling phase at either the test strip nor out at Wendover. And the final roll was done with that very same steel roller now operating in static mode to create that final smooth surface. So 96+% density has been commonly achieved, and the roller patterns have been pretty consistent across the state. Not everybody is following that exact roller pattern that I just mentioned, but the state has gone anywhere from thin lifts as thin as 1.5 inch to even greater than 6 inches compacted thickness in one lift now. And again, the density requirements have been easily met almost exclusively. It should be mentioned that there is a longitudinal joint density requirement in Utah as well. 94% is that requirement. Lift thicknesses of 2 inches plus are held to that level. There has been some struggles on a few projects on the 2-inch thicknesses of achieving that 94% density. It is my understanding that the contractors have, of their own volition, chose to cut back those, much like you might see on an airport project. And with the cutback of that material, they're finding the 94% density tends to be no longer problematic. To date, we haven't seen any project failures. We haven't seen any notable distresses at any of the installations around the state. So some other facts. In 2024 is when this material really took off in the state of Utah. They put out over 500,000 tons in terms of bid that year. They found that the contractors were really pushing for this as well. In 2025, so last year in Region 2, that Salt Lake City region once more, fully 70+% of their mixtures were this highly modified low air void mixes. The one-time main advocate for additional Portland cement concrete, turns out to have been the regional materials engineer in Region 2 who picked the Wendover location. He is now retired, but in the last year and a half of his career, it was notable that he, who once was promoting more concrete, was now switching concrete projects to this technology. And again, exceptional performance throughout. In terms of cost, Howard Anderson was kind enough to provide me with cost data. I'm showing you a comparison between the typical hot mix asphalt. That's going to be a super pave 6434, SMA, which was once the dominant mixture for high stress locations within the state of Utah, and finally the highly modified materials. Notice that in 2023, the cost of the high mod actually was less than the 6434. That in part can be primarily related to most of the projects with the high mod had relatively short haul distances, and so additional cost was encumbered by super pave in terms of haul. That isn't directly reflective of the material itself, but since we did not have the ability to filter that out in those projects, we see the raw numbers of 125 and 117 respectively per ton. In 2024, high mod, as expected, is slightly more expensive per ton than the super pave. And then a really interesting thing happened in 2025. SMA was once the most dominant hot mix in terms of tonnage in the state of Utah. And in 2025, as you can see, no SMA went down. There will be some SMA that goes down this year in 2026. It's not going to be exceptionally large tonnage. But the reality is that SMA has become almost an afterthought in Utah because of the high performance of the highly modified material, as well as the embracing of this material by the contracting community. You'll also notice in 2025, I show you two different prices per ton for this mix. That is because, excuse me, there was one project that was mixed in the Salt Lake area and had as much as a 6-hour one-way haul to the Four Corners area in the extreme southeastern portion of Utah. And so the two costs that we see there, the 140.31 per ton is all of your highway mixes. The 138.77 is with that additional haul length project, which by the way was 200,000 plus tons being filtered out. So almost a buck and a half savings. You might a little over a buck and a half savings per ton because of that exceptionally long haul and large tonnage project. And so that equates to about 11.3% difference in cost between super pave as filtering out that long haul project and the high mod material in 2025. Where has it been used? Well, kind of everywhere in Utah. It has become the dominant mix. I mentioned over 500,000 tons were contracted in 2024. Last year, they placed a little over 600,000 tons, and we're seeing it in thick lifts as thick as 7 inches compacted. We're seeing it in very high traffic areas. Wendover is the shining example of that at the truck weigh station. Wendover is certainly a high stress. We've seen it in thin lifts, including 1.5 inches on top of bridge decks. We have overlaid both rubbleized and unprepared PCC on I-15 and 215 respectively. It has been used in truck climbing lanes on the interstate as well as U.S. highways in some of the steeper mountainous areas where they've really struggled to keep an asphalt mixture of long term. They have high traffic intersections, including one that is coming from a mine in the mountains in a downhill configuration to a stoplight, where the loaded mining trucks do have to come to a stop. As you might imagine, that has been very problematic as well. And they're even using this on low volume roads. Utah had once embraced SMAs, including on low volume roads. So I mentioned how they used them in their high stress locations, but it's not exclusive as they used it in low volume roads in their southernmost region as well. This technology is certainly catching the attention of other Western states as well as outside of the Rocky Mountain region. I have sent this specification as far away as New Zealand for the Utah spec. Montana, we laid our first trial in Bozeman, Montana on North 19th. Those of you who may be familiar with Bozeman, that is the interstate exit that services Montana State University. It was about a 19,000 ton. The project was originally going to be utilizing a massacre grade and a 9.5 millimeter gradation. This was the 9.5 was before Utah had come up with a 9.5 gradation of their own and specification. The bottom line is that the mix design with those two materials struggled. A lot I could talk about that I don't have time for in regard to that. The short version is that they did have struggles, and so approximately 2 weeks before the project was to begin paving, a change order was initiated where they dropped the Utah spec in, utilizing the 7634 and 12.5 millimeter. The contractor was awarded about a $500,000 change order. So even though the original project saw a notable bid below the engineer's estimate of approximately 75%, with that change order, it came in rated about the engineer's estimate. The project itself was successfully paved and densities were very easily achieved by that contractor. There was an issue, however, with the binder. It did have, excuse me, a rotational viscosity that exceeded the typical Utah spec. They did drop the Utah spec in, but they did not hold that binder to it in terms of rotational viscosity. And the upshot was that the contractor had some issues with their pumps getting hit with some high amperage, and therefore they had to essentially choke their plant back to keep the amperage on the pumps at an acceptable level. And so the production of that plant was roughly cut in half. That equated to longer paving time, but the upshot is that the contractor, who did have some notable things to say in regard to what happened on that, has been proposing to the Montana DOT the option of switching some projects to this technology. And so while they may have had some complaints, they seem to have liked it well enough to where they are promoting it now within the state. Colorado has a project that will be going down this year near Rifle, Colorado. Again, they're emulating the Utah spec. Some of the other western states that I work in, Idaho, most notably, then Johnny's home state of Arizona. Mark Blow, our engineer out of South Dakota, has 2 states, Missouri and North Dakota, that are also looking at this. I can tell you that I've had conversations now with approximately 12 different states that are looking at this technology and trying to emulate the highly modified low air void system that Utah has been so successful with. So with that, I'm going to turn this back over to my good friend Johnny, who's going to take us through the rest of the presentation. Take us away, Johnny.
Thank you so much, Dave. And our fifth and final state was Virginia Department of Transportation, the Commonwealth of Virginia. So for those who do not know, Virginia DOT oversees the third largest U.S. public roadway network. So we're talking about 129,000 lane miles. And there is a big portion of asphalt being laid on top of jointed concrete pavement. So when we talk about interstate, we're talking about over 1,000 of that 5,000 lane miles, so over 20% of that. And in the primary network, we do have about 1,100 lane miles of that 22,000 lane miles. So when Virginia DOT wanted to approach the use of HP technology, their primary concern was to try and, first of all, increase the cracking resistance of the mix being laid down on top of the jointed concrete pavement, as well as mitigate reflective cracking and try to delay and resist that distress as long as it could. So the first project actually was in 2014, and that was on in a rural area. It was a subdivision. It was just for trial purposes. Probably in most cases, it was not really the use of HP was not intended to, mitigate cracking in general, reflective cracking in particular. But then after that, starting in 2015, you see that technology was employed on a lot of of interstates. So in this table, for example, we're computing the various routes and sections that were used on which HP was used to mitigate reflective cracking, except one where we did have a bituminous material on top of an existing asphalt. So these are not all projects that VDOT has constructed. This list is as of 2018. I would assume double of these on top of these. There were about double of these sections constructed between the 2019 and the 2025. Taking you through a brief and a quick example for the sake of time on I-95 southbound in Prince William, you will see that was a 2-inch of a dense graded surface mix. It was 12.5-inch mix constructed on top of a jointed concrete pavement. So that was constructed in 2015, and then the year prior of that, in terms of rehabilitation, was in 2009. So through the pavement management system, there's something. So VDOT uses or employs what we call the critical condition index, and that index with 100 referring to an excellent pavement performance and a 0 to totally fade performance with a cutoff limit of 60. So what I want to say, based in the left graph, based on the collected data, there was a stone matrix and an asphalt layer, an SMA built with a conventional PMA binder compared to a densely graded compared with HP. You will see a much higher critical condition index from construction as well through the first year of performance. You will notice as well the decay of the CCI, or the rate of decrease of that CCI, is way lower or much slower for the HP layer compared to the conventional PMA. You can collect all kind of distresses. Since reflective cracking was the major distress of interest for this project, you will notice that the amount of reflective cracking was significantly lower for the HP section compared to the PMA section, and you will see the rate at which the reflective cracking is increasing is much slower and much lower compared to PMA. So based on the collected and documented PMS data of this project and all the other project, HP sections showed very promising performance after 5 years, and even 7 and 8 for some sections, regardless of the traffic level and the pre-existing pavement condition. So the study involved looking at every and each section case by case, but for the sake of time, we compiled all critical condition index data for HP section versus PMA, and we plotted these data function of the duration in years. And as expected, you expect that your CCI gonna decrease within time. So you'll see in this plot for the red, that's the HP mix, the decrease happened at a lower rate, and you will notice a CCI of 60 is VDOT's CCI of threshold. So if we look at the 60, you will notice an 8.3 years for HP mixes compared to 6.2 years for PMA mixes. So you will notice an extension of about 34% in terms of performance life. Well, I'm going to put a caution here. While these numbers might look much lower compared to typical numbers that we see on overlay, I want to remind you that these are 1.5 inches or 2-inch overlay on top of a jointed concrete pavement that was not necessarily treated to the best prior to construction. So all these will factor in. And then if we go with the rule of thumb of reflective cracking of that 1 inch per year, I assume these numbers are pretty much high compared to what we typically see with reflective cracking on conventional overlay on top of jointed concrete pavements. So some lessons learned, general lessons learned, and effective practices, whether from Virginia DOT as well as the contractors and so on. They recommend consulting with supplier regarding any handling instructions, and especially your polymer supplier. During that time, when we visited with contractors, they reported recommended storage time of 3 days or 3 nights. In that case, contractors should have some backup options for HP, binders, maybe blend down option in case, you had some weather restrictions or some breakdowns of machinery that delayed you of executing the job. Also, according to the contractors, their wax-like products that are typically used to reduce binder viscosity are not recommended. They also recommended the use of a material transfer vehicle, MTV, to help establish a continuous paving, and that will lead to a higher quality and a smoother mat. And always, VDOT personnel recommended, as well as a contractor, checking the quality of HP binder, upon delivery and even during production, by sampling and doing an extra testing at a frequency that's slightly higher than the typical frequency of testing asphalt binder for conventional jobs. So there is a lot of effort and a lot of information for Virginia. So this QR code will take you to a study that was completed around the 2021-2022 timeframe, and that has all that data together. So if you check your chat, our moderators provided links to memorandums for our virtual visits with the 5 state DOTs. So if you click on these links, you can download. These are about a 15, 17-page PDF that summarize or provide all the information that we compiled, but for the sake of time, we had to provide a summary of that information in this webinar. So now we're going to move to the last part, which is the strengths, weakness, opportunities, and threat, the SWOT analysis. You'll see a QR code here as well as a link to our technical brief that has the details of this analysis as well. You can access that. Just check into your chat and then you will have access to that link. So starting with the strengths, these were divided into 2 categories, people versus HP technology. When it comes to people, we talked about the support from Federal Highway Pavement and Materials Program, and then assessing and deploying this, assessing the effectiveness of this technology or the readiness of this technology, as well as deploying it, and then looking, at the barriers and all aspects of that technology is a clear example of the support of Federal Highway, and then this cooperative agreement is a clear example of that. State DOTs, you will see a lot of interest. We took a look at that map between the 2021 and the 2025. We've seen that increase in the number of states trying to experience with such technology, as well as the industry and research community. There has been a lot of work documented, whether in the lab or in the field, about this technology and the enhancement in material properties, as well as performance characteristic, as well as a major support of industry. Dave just took us thoroughly through the experience in Utah, and he emphasized about the important, support and that synergy between the industry as well as the government. Talking about HP technology, again, a lot of work exists in the literature about enhancement and performance. We've noticed that the use of that technology did not require having a new design method or machinery. It's compatible with whatever is existing and we use from a day-to-day practice. And every day there's a lot of advancement in binder modification, and that's going to help positively towards the high polymer technology. It's always great to highlight some weaknesses, and do that assessment and try to turn these weaknesses back into strengths. Also, these were divided into people as well as the technology itself. Under the people's umbrella, there's a variability in expertise, and you will see, for example, the experience in, the state of Utah is totally different than an experience in a different state, and that's expected. Limited contractor familiarities, especially those states that are trying, to experience a little bit with the HP technology. This may require a little bit of training, and other educational opportunities, such as this webinar and many other of the documents that are published underneath this project and published by even other, organizations, so they don't have to start from scratch and they can familiarize themselves with the technology. When we talk about the technology itself, the primary and a very interesting factor is the lack of standardized definition. But I've had a slide that had the 5 specification for 5 state DOTs, the one we visited with. You will notice that these specifications are totally different. So that is, how do we define a high polymer? That remains the very important question. Higher initial cost. Dave alluded to that case by case, state by state. I'm going to have a summary table in a couple slides looking at it. Even though this is a weakness, a lot of state DOTs were able to justify an extension and performance life that was able to justify as well the higher initial cost. So we're looking more about a benefit cost ratio rather than just a cost assessment. Specification variability that entails to the standardized definition. Potential workability concern. I saw a couple a question in the chat. Chat will allude into that during the Q&A and how some of the contractors were able to handle that and how the state DOT were able to address the topic of viscosity to begin with and a potential, associated workability concern. And then at the end, optimization challenges. It's all about the polymer type being used, the dosage, the compatibility between the resultant binder as well as the aggregate available in a given area. Tank storage stability, we'll talk about that a lot, and shelf life. And the various performance of this technology in different climatic region and environmental condition. This is a very important slide about nomenclature. In the case of this technology, nomenclature matters and matters importantly. We see a lot of the acronyms refer to the high polymer technology being used interchangeably. While the primary objective might be similar, there are enough nuances that make these a little bit different. So the hope from this slide is, to bring the light about the differences between these various nomenclature. For example, the high mod or HAMC, that's the high modulus asphalt that was originally developed in France, and it uses very hard, stiff binder combined with a high proportion of binder and dense graded aggregate. Then we do have the HIMA. That's the high polymer modified binder. That's a proprietary product of Kraton Polymer. Then you have the high polymer binder HP, which is a non-proprietary, a more general way of defining these binders that was adopted by the Asphalt Institute, Florida DOT, Virginia DOT. Then you do have a high performance grade, which is a recently introduced nomenclature in Texas, HPG. And then finally, you have the high mod, the highly modified asphalt mix that was adopted by Utah DOT. And I believe if we keep on searching, there might be many additional nomenclatures that are added. Again, this is a summary table of the usage and costs. I know Dave went in details over the usage and costs of the first 4 states. I did the Virginia. You will notice in all of them there is an increase compared to PMA. But again, a lot of these states were able to justify the extension and performance life and justify that cost increase compared to PMA. Just to reiterate what they've mentioned about Utah, you will see an increase of a 6.6% compared to their conventional HMA. However, for the sake of comparison, the SMA entails about a 27% increase compared to the conventional HMA. And all of these data are based on analysis conducted as of August 2024 when this data was compiled. Some opportunities, again, federal state funding support. This project is a clear example of that. Growing demand for high performing pavements. We have a growing, amount of load in this world, as well as the magnitude of that load. So all what we need is a better and a higher performing pavements. We do have a lot of advancement in testing and characterization that can shed the light about, the improvement that this technology may bring. Collaboration and knowledge sharing. This is a great example here. For example, the webinar collaboration. Dave highlighted in details about that synergy between the state DOTs, the contractor, supplier, and so on for the success of the various projects. For example, conducted in Utah and even the remaining states that we visited with. And then field performance. Some of these states we just saw for example, the Commonwealth of Virginia, Virginia DOT, with the data there, it shows that it's working in the field, enough data, and then there is that extension in performance life. Finally, looking at the threats, supply chain and material availability remain a threat for this technology and any other technology. Budget constraints, and that's the case in many of the states. Well, they tell you, I don't have the budget for that initial cost, and I would rather invest that money into, conventional technologies that I'm conducting, and then paving as many routes or lane miles as I can. Workforce training needs. You want to make sure that if you haven't dealt with that material, to get a little bit of training, or at least, familiarize yourself with the material before going big into a project. And then state priorities. It could be as simple as, for a given state, this is not a priority at the moment for this technology or any other technology. Now, the hope is to turn the threats into opportunities. Finally, looking at the key strategies for implementing HP mixes. First of all, it's a performance-based approach. And I had that in an earlier slide, that it's not defined based on polymer content, but it's more performance-oriented, binder spec, supports innovation, cost-effective sourcing. It's application-specific use. We've taken you through various case studies in the 5 states that we elaborated on. And then you've noticed that that technology was used for various purposes to address various, maybe key distresses. It was an application-specific use. The intention here is to use it to extend performance life and not a substitute for a poor structural design or maintenance. Cost-benefit evaluation. Again, we've seen initial higher cost, but we were able to justify an extension of performance life. So look more on the cost-benefit evaluation and not the cost component by itself. And finally, feedback loop. Simple example was Utah. They've had a given experience. They took a step back. They assessed, all the data compiled back in the days. They made enhancement improvements, came out with the high mod spec, relooped it back, redeployed it, and then got positive. So always integrate lab testing, field data, spec updates for continuous improvement. With that brings us to an end of the presentation portion itself. I do have the contact information for the sake of recording of myself, Dave Johnson, Dr. Ilker Boz, Dr. Stacy Diefenderfer, both from VTRC. If you have any question, feel free to email us. And then with that, thank you for your attention. Really appreciate it. And Tim, I'll hand it back to you. Thank you.
All right. Well, thank you so much, Johnny, and thank you so much, Dave, for such a thorough presentation. Very good. I'm going to go through a few of these questions, and I'm going to call out a slide number. Sometimes if there's a slide up there, it helps give the context to the question. The first slide is slide 50, if you could go to that one. And this question, I think John, if you just type 50 enter, it might just go there directly. But this question came in about the Hamburg wheel test temperature. And we may have answered this already, but I just wanted to make sure you had an opportunity if you want to add anything. What test temperature do you use for the Hamburg wheel track test? Is it the same as normal mixtures, or is it different?
I'll go ahead and jump on that one, Johnny. In Utah, they've made the decision to settle on 54 degrees C. Thank you, John, from Montana DOT, mentioning what they're doing at 56 degrees C with our upcoming project. A lot of the states are still doing 50, but recognize there was also 2 states that we mentioned that are using the APA. Those are at 64. A little bit different device, obviously, and some different parameters, but those are the temperatures that we've noted thus far.
Very good. Next, slide 53. Here seems like we had a slew of constructability questions, and I think slide 53 gives a nice shot of the construction process. Is there any issues or problems with recyclability of the high polymer mixture?
Go ahead, Johnny.
You can give it a first shot and then I'll follow up, Dave.
Yeah, one of the things to keep in mind is this is fairly new technology going to these higher loadings of polymer. And so the most that I can talk about is recycling of typical polymer modified material, which has a long history of success. We'll have to wait and see on the highly modified as to how that may or may not be any different. I don't anticipate one that the need to recycle it will be as much because of the longer performance life. The other thing that I would point out is that these are very rich materials, and recycling richer materials tends to be done more successfully than drier materials. And so I don't anticipate notable issues with that. Johnny, go ahead.
Thank you, Dave. Just one comment to add on what you mentioned recently. I mean, within the last couple of years, Florida had its first HP project mill. And
Hmm.
then there is an assessment, thorough assessment of the binder properties, extracted properties of the extracted and recovered binder from these wrap stockpile, and then trying to assess what could be the impact on, resultant binder once that wrap is and included in the mix, as well as on the mix design and the performance in general. So these results are yet to be present, and this is being conducted in Florida with a major lead from Florida State University. Thank you.
Okay, thanks. And then a related question that came in was if you do have some wrap that's this high polymer mixture wrap, can you put that back in a premium surface layer?
I'll jump on that one to begin with as well. As I mentioned, the state of Utah allows up to 15% wrap in their mixtures. Again, that's by mass, not by binder replacement. And this is a first for the state. And so, again, I would not hesitate to utilize highly modified wrap in the future in surface mixtures. One thing to be careful with is making sure that we don't push the wrap limits too high too fast. Let's make sure that we do engineer them. And an entirely another topic is the whole issue of rejuvenation, and we could go down a rabbit trail on that, but I'll stop there.
Very good. Yeah, we'll move on to the next question. It relates to workability, and inherently the polymer network is going to drive up binder viscosity, and that could create some challenges during mixing and compaction, forcing higher production temperatures, which may risk polymer degradation. Do you have any strategies or emerging additives you might recommend to cater to this workability issue without compromising the high polymer binder?
So
Go ahead, Johnny. Can you jump on this one first?
I'll jump in a general. I want to first elaborate a little bit on the workability limitation or challenge that we might face before addressing the question. So there's always that worry about higher viscosity when you're dealing with a high polymer binder in general. And when the study was completed for Virginia DOT back in 2021, binder data properties were compiled while your typical superpage spec allows up to a 3 Pascal second. However, there is a caveat that that requirement could be waived with the approval of the engineer. Looking statistically at the various data of the various binder, sampled throughout the years, mainly two binder suppliers, hopefully from two similar, two different sources, it was found that that 3 Pascal second will go up to about a 4.5, 4.6, 4.7 Pascal second. So during that time, the department felt comfortable in changing the requirement from 3 Pascal second to 5 Pascal second, was still giving the caveat that if this is not fulfilled, it's up to the engineer to make that decision. And then there is a law that goes with, the polymer network structure of the binder itself, as well as the testing condition, the rotational viscosity and the 135 degree Celsius or 275 degree Fahrenheit, test requirement that may not be applicable for HP technology. You saw in other states as well, like Ohio, they allow all the way up to 10 Pascal second, and I'll let Dave elaborate on Utah. Just trying to address the question, the use of warm mix additive, at least based on my experience in Virginia has proven to help with that. Other states as well, they do have a limitation on the upper temperatures mix at the plant. For example, Florida does not allow anything that goes above 340 degrees Fahrenheit, for example. And another thing that comes to my mind at the moment is correct planning. You should be able to plan prior to the project very thoroughly so you don't have any delays. So if you are, producing your mix at that 325 or 330 degrees Fahrenheit, you do not need it to go higher to buy yourself time, and then that will help you with a smooth paving operation. So that's to start with. I'll pass it to you, Dave.
Yeah, thank you, Johnny. The only thing I will add is certainly the Utah experience. First of all, with all polymer modified materials, especially when you start getting higher polymer loadings, recognize that increased binder temperature, especially in storage, can be very counterproductive. You can increase the cross-linking rate and therefore increase the viscosity as it sits in the tank. I call it viscosity creep. And so you want to be careful to work with the supplier and the polymer supplier in particular to make sure that you are not exceeding their recommendations of that temperature to avoid that scenario from occurring. The other thing that I'll point out is that in Utah, all of the mixtures that have been produced to date, all the projects, with the exception of one, do utilize a warm mix technology, not for the anti-strip or the warm mix capabilities per se. Utah is a lime state, and so they're using it as a compaction aid. And that has been very consistent to where now it is standard practice. I saw there was also a question in the chat that I'll go ahead and jump in on with the material transfer vehicle. That's also a requirement that's happening in Utah as well, especially on the long haul projects. Getting that remixing, I think, is very important to cut down on the potential thermal segregation. There was also a question about tarping. I would certainly tarp my trucks if I had any sort of distance, regardless of the atmospheric conditions. But another piece back to the workability is contractors in Utah report to me, and the city of Salt Lake, for example, has had projects. The first project in Montana was an urban project where handwork was necessary as well. The Utah contractors report that handwork with this mix is very similar to what they saw with the 6434 super pave mix. Recognize that, yeah, this is a stiffer binder, but it's a higher asphalt content and it's a fine graded mix. And so you get some advantages within this system versus the super pave and some disadvantages. And the upshot is that the contractors reported to be relatively similar.
Hey, very good. See, we've covered the tarping question. If we go back to slide 50, here we're looking at the mix design. Has anyone used the high polymer mixture without 100% manufactured aggregates?
I can say that some of the states that are investigating emulation of the Utah system have done some work with allowance of small percentages of sand, less than 15%, I think is about the maximum. And there has been some difficulty with their rutting apparatus, whether it be Hamburg or APA, when they do allow the sand. There's a Midwestern state, for example, I won't say which one, that allowed sand that was struggling to meet Hamburg requirement. They eliminated the sand, and the issues went away. And so it's entirely possible that you may be able to do that, but I would rely upon the rutting tests to determine whether or not we have confidence in the field performance. You're buying a premium mixture here, and therefore let's be careful not to compromise that premium mixture, even with a small amount of sand.
Very good. Next up is a comment related to cooling. And you may have your own comment you want to add as well, but it takes time to cool down even after paving, but it becomes really hard after cooling down. That's why I think the haul time was relatively okay. So I don't know if you want to add any of your experience based on that comment.
Yeah, these mixtures, one thing that we didn't talk about with thick lift is that you need to be on your A game when it comes to paver operations. Any little mistake you make is going to be accentuated in a degradation of the ride. Therefore, the need to do post-construction grinding to achieve smoothness, especially with thick lift paving, can become an issue. The milling contractors in Utah report that milling of these highly modified materials is very similar to what they've experienced when they've been milling concrete. And so they're going through teeth a little bit faster, and it's a slightly greater cost per unit to mill this material. It does become very hard, as was stated. Certainly not as hard as concrete, but definitely more so than typical asphalt.
Okay. Next question about MTVs. I think you mentioned previously, but a side question came in terms of windrow paving. Would you be able to do windrow paving with this?
We did in Montana. And Utah does windrow paving, but they go run it through an MTV.
Very good.
So
And
the
then,
Tim, if
oh,
you
go
don't
ahead,
mind,
Johnny.
the only thing I can add for not necessarily the high mod mix, but more the HP mix, when we visited with the contractors back in 2021, all of them recommended using an MTV on a jobs that requires or that features the use of a high polymer mix, and that's to have a smooth, good quality paving as well with a smooth surface at the end. That was one of the best practices or effective practices recommended by contractors in Virginia back in 2021. Thank you.
Good addition there. Thank you. Next question is wondering about the storage period for some isolated area construction that happens to have long haul distances. Islands.
Are they talking storage of the binder, Tim, or the mix? I'm curious
But I
about.
would try to answer both if you were able to. I was wondering the same thing.
Sure. Um, Storage of the mix is going to be somewhat similar to what we'd see with other mixtures. We need to have adequate temperature to be able to get density. When it comes to field construction, that's always the key factor that I'm looking at in terms of acceptability of that material. Certainly, smoothness comes into play as well, but I'm really keying in on density. When we were talking about storage of the binder itself, there historically has been some notable issues with the storage stability of highly modified materials. I will compliment our suppliers in their advancement of their chemistry. That has become less of an issue, but it does take some experience with your materials, your base binders, as well as the modifiers that you're utilizing to come up with the right combination to be able to achieve that. I can report that the 2017 projects in Utah, for example, had some issues with the storage of modified material. Whereas today, with so much experience and so much tonnage having been produced, I don't hear anything negative. In fact, I hear some remarkable storage times that I won't repeat because I don't want situations in other parts of the country to be going, well, in Utah, they're getting this. They're very favorable. And quite frankly, 10 years ago, I would have said impossible to achieve. And again, the chemistry has come a long ways. Thank you, suppliers, for your work in that arena.
So the only thing, if I may add to Dave, in addition to a lot of improvement and the way polymer are formulated, as well as resultant binder. If I understand the question correctly, I believe question is intended. Let's suppose a given island is interested in an HP or a high mod mixtures, but they don't have a binder supplier that can deliver a binder on that island. Let's suppose I'm just giving for the sake of an example, a recent communication about the state of Hawaii, and they wanted to hold, HP binder and vessels, for example, from Florida all the way down to the state of Hawaii. That will take multiple days to make it there. Will you be able to reheat the binder, pump it? Will the binder have maintain the same properties and so on? Uh, 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 so There's been a lot of discussions. I'm gonna limit my intervention up to this level, and limited to it's yet to be determined. So
Fair enough. The next question showed up on slide 68. And on slide 68 is the PG 76 minus 34, formerly called PG 76E minus 34.
Hmm. Oh, I think
Yeah, so
go ahead, Tim. I'm sorry. Go ahead.
I was just going to repeat the question. Is PG 76 minus 34 you see there, is that formally called PG 76E minus 34?
No, I think that a little bit of confusion is arising from the fact that we started in Montana with a massacre grade. We are a massacre state. Our future projects, I believe, are all going to be massacre grades. Um, there was some issues at getting the mix design to pass under the original spec that the Montana DOT had with the contractor. And therefore, with about 2 weeks prior to paving, there was a switch to the Utah spec, which included a PG 7634, an M320 binder. And so the shift was made to a straight PG grade versus a massacre grade. And I think that may be where the confusion's arising.
Got it. Okay, that's good for the clarification. Now, staying on this slide, I'm going to skip to this next question that came in. So, are all of these current and future projects being considered to use the high polymer asphalt as a requirement to meet the spec of these projects?
Yes. Very quick answer.
Very good. Okay, fair enough. And then this, I skipped over this one comment we'll go back to, but that relates to slide 42. And I think Oklahoma has a similar example. In the UK, with overlaying severely cracked concrete, a 6.5% SBS binder was used in a SAMI and an SMA surface course. And the solution was very cost effective compared to replacing concrete that's been out there 10 years, no signs of distress. I thought this was a nice comment that related to the Oklahoma experience. And I don't know if you have any comments you wanted to mention here.
Thank him for the comments. I appreciate the information.
maybe the only thing to add on Oklahoma, we go back to the history. So the first section on the NCAT test track, the base layer employed an Oklahoma mix, and that was emulated the rich intermediate layer that Oklahoma was very pleased with the performance. And then the year after, they decided to go and pave about, I believe, 2 miles on I-40 using the rich intermediate layer, and they've seen a fantastic performance until now. And then we've taken a look at as well the tonnage and the frequent use of such mix for the state of Oklahoma. So
Good. It's interesting to see how the performance in the UK and Oklahoma model each other, and it's both very good.
Mhm.
Next question relates to preventive maintenance schedules. So, if you're using a high polymer binder or mixtures, what would you say about your preventive maintenance schedule?
Well, speaking from the Utah experience once more, since we have yet to have any distresses show up on any of the projects, I can say that we are seeing an extension to the time frame to when we will need to do the preventative maintenance. And I think, Johnny, you might be able to speak to the Virginia experience to give an even more thorough answer.
yeah, the only thing I can add, we did not look thoroughly into preventive maintenance, but based on the data collected, there was an extension in performance life, which indirectly will delay the need for preventive maintenance when these type of mixtures are being used. But just looking at data or percentage bulk, I don't have that data. So
Fair enough. Next question, I think, relates to slide 26, We're going to go back to the discussion on the open graded friction course. We got a question about anyone having a specification using this high polymer modified binder in an OGFC. We did get a response from Florida. Greg, thanks for chiming in, that they designed the mix and then substitute a HP binder, and it does really well in the Cantabro test. But I don't know if either of you might be able to add anything to that, helping out Alabama and Florida.
So the only thing that I may add is when it comes to high polymer technology, there are two distinct way of approaching the mix, whether it's open graded or density graded or even SMA. For example, Virginia DOT uses SMA with HP. They designed their mix using the conventional, way of designing the mix, and then they just do binder swap, and then they get that extension and performance life. And we've seen that in a case for Florida DOT with the open graded friction course, and it showed a significant extension and performance life. And then we talk when it comes to the high mod, it's a system. It's a combination of, the enhanced property of the binder being used, as well as a different way of different parameters for a given mix design. So this is a system coming from the aggregate, the binder together into the mix, and is not necessarily a binder swap. So just wanted to elaborate on that because some people just get confused, and I mean both seems to show positive implication and results, but again, you got to tailor what you use towards the needs that you have in your state, as we mentioned towards the end. So
The only thing I would add to Johnny's great comments, at the Asphalt Institute, our magazine, which you can get for free, and the archives are available for free. There was a nice article jointly written by Doctors Grover Allen and Buzz Powell on extending the life of OGFCs, as well as there's in this next edition that will be coming out shortly, one of the myths that Buzz and I addressed, again, with Grover's help in particular. Dr. Grover Allen's help in particular is also dealing with longer life performance of OGFCs, especially as it relates to this topic of highly modified materials. So I would encourage you to look at those works.
Okay, very good. Jumping to slide 80, here we have a comment that consistent terminology is critical, not just for this, but for the other areas, for example, biobinders. I don't know if you have any additional comments you want to add. What should we call it? Or just as a product with many names.
that's the $1 million question too. So
Yeah.
I believe at this level, the intention is to bring awareness to everybody that even though the main intent might be similar, or all these are merging towards the same objective, there are enough nuances that makes these various nomenclature, or call them maybe sub-technology, or they all come under the umbrella of HP in general, that makes them different. So well, it's yet to be determined. Maybe we call them the H, and the H will stand for the habush and not the high. So we'll see.
I'll just say that there's a lot of work being done. This is a recognized need by a variety of organizations, ourselves at the Asphalt Institute, the National Asphalt Pavement Association, the Transportation Research Board, FHWA. I could add more to that. There is a concerted effort that's happening to try to come to an agreement within the industry on nomenclature, and hopefully we can do that.
Very good. And I think we have an important comment here. Thanks, Bob Klutz, for providing this. But just to be clear, HIMA, the highly modified asphalt TM, is a registered trademark, not a proprietary product. So appreciate that.
Thank you, Bob.
Thank you for correcting us, Bob.
Yeah.
And then the next question, if we can jump back maybe to slide 12, are the BMD tests picking up performance improvements of these mixtures? Obviously we think of improved riding resistance and improved cracking, but particularly with the cracking, which one of the BMD tests have you seen pick up the benefits of the high polymer mixture and binder?
So As part of the effort that was conducted for Virginia DOT back in 2021, there was look as well on an assessment of material from projects that were produced and placed in the 2019 and 2020. And these cover sections that were not presented in the table that I provided in the slide. And then during that time, we looked specifically at performance tests that are as part of the balanced mix design framework for Virginia DOT itself. And then for those who do not know, Virginia during that time employed only three tests. For durability, they used the Cantabro mass loss test, and they do that test on the design pills. So you're looking at an air void of about 4%. And the ideal CT, or what they refer to as the IDT CT, indirect tensile cracking test, as well as an APA. Virginia has been an APA state since the early 2000s. They conduct their APA at a 64 degrees C. So with the Cantabro and the APA, it was very obvious the improvement in performance properties. When it came to ideal CT for densigrated, it showed similar performance, not even lower. But there are a couple things I want to mention here. The testing happened on a reheated mixture. So that mix was cooled down to room temperature, sampled at the plant, cooled down at the room temperature, then reheated, then specimen were made, then they were tested. So that's one thing. That reheating could have impacted that data. Number two is there's still a lot of effort ongoing about, the ability of these tests in capturing, the impact of polymer modification in general to begin with, and then a high polymer modification in particular. One
Mhm.
last thing I want to mention, VDOT uses SMA with HP as well. So they just do binder swap in their SMA and they use HP. All these tests were able to show improved performance of SMA versus dense graded, and an HP versus conventional for the SMA. So
Mhm.
just wanted to allude that. I know there's a lot of effort at the moment trying to look at, looking at maybe a different way of analyzing the data collected by these cracking tests in a way to be able to capture enhancement due to polymer modification in general and high polymer modification in particular. So I'm not sure, Dave, if you have anything to add. I wanted to share Virginia's experience at least.
Yeah, and that's fantastic. The only thing I would add is not ignoring the great work that's being done at many of the DOTs, because there's a lot of internal work that's being done that isn't necessarily getting published. The work that's being done at some of the different transportation centers and universities, so NCAT, TTI, UNR, Rutgers, there's others as well. I would encourage you to look at some of that information. It is definitely reflecting a lot of what Johnny was talking about there, and you can find documents and um, um, uh, both success and challenges with some of the tests.
Okay. Then next up, if you have a 1.5 inch overlay, was the nominal maximum aggregate size is at 12.5 millimeters or 9.5 millimeters?
The short answer is yes. We've got both 9.5
Okay.
millimeter, inch and a half overlays, as well as 12.5 millimeter, inch and a half overlays. Recognize that these mixes are fine graded mixes. And so we're right at, with a 12.5 millimeter, that half inch, we're right at the 3-to-1 ratio. That is the minimum thickness that we would encourage. And so excellent observation. But yes, both thickness has been achieved with both gradations.
Very good. And then slide 30, maybe we'll wrap up. We got to have a couple binder questions here with our high polymer binder. Could the poker chip test provide a better means to characterize the strength of the polymer network? What are your thoughts if you're going to specify a high polymer binder?
If I want to start, thank you, Gary, for this question. I assume Gary Fitz asked the question. Uh, the way my experience with the poker chip is limited. That's why I'm gonna pass on this question. But I would assume if it was able to pick up on the performance and been useful for conventional polymer modified, I don't see why not for high polymer modification. Dave, I'm not sure if you have anything to add on the poker chip. So
My experience with the poker chip might even be less than yours, Johnny. It is definitely an evolving and it's a test that is gaining attention. I'm just not expert to be able to comment on it.
Fair enough. And as we look at this criteria, we see 90% minimum mass occur recovery appears to be very common. Is that based on performance? I mean, why wouldn't somebody say 75%? Any thoughts there?
I will say that it is a premium mix. And whether we're talking massacre recovery or elastic recovery, 90 is the number that seems to rise to the surface, no pun intended. And so um, if your experience indicates that allowing a 75% recovery still gets you the performance characteristics that you're seeking, then I'm not going to argue against it. But thus far, 90 has been the number that has been settled upon, perhaps because we're conservative engineers, but the performance is indicating that that's a good value.
Yeah, maybe the only thing to add is to echo what Dave said, it depends on the state need. If we take a look, for example, at Oklahoma, they do have a 95% and not a 90%, but their
Mhm.
non-recoverable creep compliance is at a zero point 0.5, which is a typical E for other state and not necessarily an E plus or E plus plus or an HP
Mhm.
for what the other states require. So again, lack of standardized definition and various specs, but again, tailored to whatever need the state has.
Well, very good. Well, thank you again, Johnny and Dave. Really appreciate the information you presented and all the questions you provided answers to. There's still more questions. We just don't have time to get to those, but we'll try to follow up with those questions in maybe a one-on-one email as we get those compiled. Certainly sorry we didn't have time for all the questions. We thank you for your participation and look forward to having our next webinar probably in the next 1 or 2 months. And with that, I hope everybody has a good rest of the week and we'll be in touch. Okay, bye now.
Thank you, everyone.